Hey, future pilots! If you're gearing up for your PPL ground exam, you already know the aerodynamics section can be, well, a bit of a beast. But don't sweat it. We're skipping the fluff today and diving straight into high-value study material. This explainer is totally focused on propeller aerodynamics, and we're going to make it crystal clear.
Ready to ace those propeller questions? You're definitely going to see these concepts on the test. So, we're going to break them down logically, starting from the microscopic aerodynamic level straight into the cockpit. Let's get right into it.
Section 1. The anatomy of a rotating wing. Let's hit the basic terms the FAA really wants you to know.
Okay, so a propeller blade. The absolutely crucial thing to remember here is that a prop isn't just a fan. It is basically an aerofoil. It's got a cambered upper surface facing forward and a flat bottom surface, literally exactly like an aircraft wing. The engine just furnishes the power to spin these little wings to transform rotary engine power into forward thrust.
Next up is the chord line. Just like the wings on a Cessna or a Piper, a prop blade has a leading edge that slices into the air and a trailing edge. Because most props have a flat blade face, that bottom side we just mentioned, this imaginary chord line is usually just drawn straight along that flat face. Keep this line in your head because it's super important for our next term.
And that term is blade angle. Basically, imagine a flat, invisible disc that the propeller creates as it spins around the hub. That's your plane of rotation. The angle between that spinning disc and our flat chord line, that's the blade angle. Oh, and fun fact, because the blade twists, this angle is actually measured at a specific point along the blade to give it a standard rating in degrees.
Section 2. Angle of attack explained. Let's see how this actually works in motion.
A propeller blade is doing two things at once. First, you've got rotational velocity, which is the blade spinning around the hub. Second, you have forward velocity, as the plane moves through the air down the runway. Mix those two together, and you get the relative wind. The angle where this relative wind strikes the blade's chord line. Yep, that is your angle of attack, or AOA.
Check this out. It's so cool, because lift on a wing is perfectly analogous to thrust on a propeller. As air flows past the spinning blade, pressure on the curved front side drops lower than the flat back side. So instead of a wing pulling an airplane up in the vertical plane, the prop pulls the airplane forward in the horizontal plane.
You can literally see this in the math. Thrust equals the mass of air handled times the slipstream velocity minus aircraft velocity. To max out this formula, the blade angle adjusts how big of a bite of air the prop takes per revolution. A bigger bite means more air pushed backward, which translates into more forward thrust. Simple as that. Section 3. Why propellers are twisted.
Okay, let's look at an engineering quirk you will absolutely be tested on. Why the twist? Well, think of a track and field race. The runner on the outside lane has to run a lot further than the person on the inside. Same exact thing for a spinning prop. The tips have to travel a vastly greater distance than the hub in the exact same amount of time, which means those tips are moving way faster.
Because the tips are moving so incredibly fast, the relative wind shifts drastically. If the manufacturer built the prop with the same geometric pitch throughout, the slow-moving hub would actually have a negative AOA, and the tips would literally stall out at cruise speed. Twisting the blade gradually changes the angle, keeping the AOA perfectly consistent along the whole length and keeping your thrust equalized.
Section 4. Understanding propeller slip. You might think a prop perfectly grips the air, but actually efficiency is usually only between 50 to 87%. Here's why. Geometric pitch is the theoretical distance a prop should screw through the air in one revolution. Kind of like driving a wood screw into a solid block of wood. But hey, air isn't solid wood, right? It's fluid. So effective pitch is the actual, shorter distance it advances in reality.
And that brings us to propeller slip. It's simply the difference between the geometric pitch and the effective pitch. It is literally just the energy lost to the air. Every prop slips a little, but as pilots, we obviously want to minimize that to get the absolute best performance out of our engine.
Section 5. Fixed versus constant speed. Let's take all this theory straight into the cockpit to see what you actually control in flight.
Right now, as a student, you're probably flying a fixed-pitch prop. It's a rigid compromise built for best efficiency at one specific cruising speed. But a constant-speed prop? That's a controllable pitch prop that automatically adjusts its blade angle in flight for maximum efficiency in almost all conditions. It's a real game changer.
Imagine you're on the runway for takeoff. You need max power.
The constant speed prop automatically stays at a low blade angle, keeping the AOA small and efficient. This lets the engine scream at high RPM and create a massive slipstream velocity. It's basically like being in first gear on a bike. You're pedaling fast and getting incredible acceleration.
Now, as you lift off and your speed increases, the relative wind changes. If the blade didn't adjust, your AOA would drop right to zero. But the constant speed prop automatically shifts to a higher blade angle, taking a bigger bite of air to maintain that perfect, small AOA. Plus, it drops the engine RPM to save you fuel and reduce wear. Pretty genius, right?
Now pay attention because the FAA absolutely loves testing this sequence. When transitioning to cruise or climb and you want to power back, you must always decrease engine power by reducing manifold pressure first and then increase the blade angle to lower the RPM. If you do it backward, you can severely overstress the engine cylinders. Throttle first, then prop.
Remember that concept flow, and you are going to absolutely crush this exam. And speaking of spins, I was actually going to tell a joke about a broken propeller today, but honestly, it really doesn't have much of a spin to it.
Okay, I'll stick to the aerodynamics. If this explainer helped you untangle these dense concepts and visualize what's happening out there on the nose cone, hit like and subscribe for more flight training breakdowns. But before you go, think about this. If twisting a blade solves unequal thrust, what aerodynamic problem do you think adding more blades to a hub solves? Think it over, keep studying hard, and I'll catch you in the next explainer.